Okay, thank you for coming, everyone. Thank you for listening to my talk. I'm Sam Livingstone. I'm an assistant professor, lecturer in statistics at University College London. And I'm going to get rid of my face now. So, there we go. So I want to talk to you today about an MCMC method, which we're calling the Barker proposal scheme. And this is joint work with Giacomo Zanella, who's at Bocconi University in Milan. So just a bit of boilerplate before we get going. I'm pretty sure most people at this conference are familiar with the Metropolis-Hastings algorithm. Everything I'm going to talk about today is going to be within the context of Metropolis-Hastings algorithms. I know that there are other methods for doing MCMC, but this is what we're going to stick to. So just to set notation, we've got a current point x. A proposal for the next point in the chain is going to be y, and that's going to be drawn from some candidate kernel q. And then we're going to construct a Markov chain by starting at a particular point and repeating this procedure in such a way that I either pick y to be the next point in the chain, which happens with probability alpha, or I will fix the next point to be the same as the current point x. And that way I'm going to generate a Markov chain which is hopefully going to have equilibrium distribution pi. So pi is going to be a distribution I'm interested in. And the game we play is choose a Q which will promote fast mixing with regards to pi. And so three possible choices for Q, which are very popular in the literature. One is very simple, a random walk metropolis. You take the current point x and you add some symmetric noise. I've just taken it from a Gaussian distribution here, and I've just highlighted two tuning parameters, which are this little sigma squared, which is a kind of global scale, and this capital sigma, which we typically call a preconditioning matrix. You generally choose sigma to be match the covariance of pi. So another slightly more sophisticated method is called the Metropolis adjusted Langevin algorithm, and instead of just adding some random noise to the current point, you also make some kind of deterministic drift in the direction of the gradient of the logarithm of pi. Right? So this makes some intuitive sense. You want to move uphill to regions of higher density but still have a bit of noise to get some stochasticity in, and you can also view it as a discrete time approximation of a diffusion process, the overdamped Langevin diffusion. And again, we've got these two tuning parameters here, this sigma squared and this capital sigma, which follow the same kind of role. And the final one is Hamiltonian Monte Carlo, which is a very popular scheme now, and it looks a little bit different superficially, but really it's not that different to Mala in the sense that you've got some dynamics that follow the gradient, which are pi invariant. In this case, they're deterministic Hamiltonian dynamics, and we're just numerically solving them. And we've got the same kind of tuning parameters here that we need to choose a preconditioning matrix, which is called the mass matrix in Hamiltonian Monte Carlo, a global sort of scaling, which we'd call the step size, but we've also got this kind of leapfrog steps. And the main thing I want you to take away from all of that discussion is that the second two methods use gradients, right? They rely quite heavily on the gradient of the logarithm of the posterior, or the target distribution, pi, in order to promote sensible sampling, and what we would usually call them is informed proposals. So we're using this gradient to inform proposals to hopefully develop fast Metropolis-Hastings algorithms. And what do we know about these methods? Well, if you take these kind of standard scaling with dimension arguments that most people will be familiar with at this conference, with d as the dimension of the state space, we tend to look at how efficient the method is in a higher dimensional setting. And most Metropolis-Hastings algorithms outside of specific setups get worse as the dimension increases, but you can see that the gradient-based methods get worse at a slower rate, right? So this gives some sort of support to the idea that in a high dimensional setting, you might want to choose Mala or HMC over the random walk Metropolis, right? But there's a crucial caveat to all of this, which is that this kind of analysis is done under the assumption that the algorithms are sort of working well. You know, everything's tuned optimally and things behave as planned. And so there's a natural question of, well, how easy is it to achieve this state? Right? So how easy are these methods to use? How easy is it to tune the tuning parameters? And I want to lean on Radford Neal here to make the point that for gradient-based methods it's not that easy. So he says in his 2003 paper on slice sampling, Hamiltonian Monte Carlo works very well provided it is tuned properly. However, choosing a step size for Hamiltonian Monte Carlo which is too large is disastrous. And I think what he's getting at is this issue that which is illustrated on these three toy one-dimensional examples, that often with gradient-based methods, if you choose a step size which is a little bit too big, a little bit bigger than optimum, you suddenly get a big cliff edge drop in the performance. And practitioners will have probably, that have used these methods, will have experienced this before, that it's extremely sensitive to the step size around about that critical value. So if you look at these plots, I've got the expected squared jump distance on the y-axis, so bigger is better. And we've got the step size on the x-axis, and these are three schemes. The random walk is in black, and Maller's in red, and ignore the blue for now. So as you can see with the random walk Metropolis, the black line, performance gets better and better and better up to a certain point as you make the step size bigger, and then you start making slightly too big jumps and not accepting enough of them, and performance degrades. By contrast with Maller, same kind of things happen for small step size, and its optimum is slightly better in terms of ESJD than random walk. But then when you choose a step size that's a little bit too big, the performance suddenly gets a lot worse, right? And this is the phenomenon that we want to characterize and talk about a little bit in order to design something that maybe is a little bit better in some sense. And you can see here that it seems to be fairly independent of the target distribution you're using, because we've got three different targets with three different tail behaviors, and we've got the same phenomenon. So why is this a problem? Because of course, you know, if you're a practitioner and you're using this, well, you think, well, okay, well, I just won't use that step size, right? I'll just stop. But we want to argue that there's a bigger issue here in that if an algorithm is harder to tune in this sense, then we've found empirically that it's harder to precondition, right? And preconditioning, and particularly adaptive preconditioning, like learning on the fly good choices of step sizes and preconditioning matrices, this really helps algorithm performance in practice. It's often something that when you're doing theory like geometric ergodicity, you often don't need to worry about these things because it doesn't affect the existence of a spectral gap usually very much, but it will affect the kind of actual speed of the method, how big that spectral gap actually is. So practitioners will know that this is a very useful tool in practice. So why does it affect adaptive MCMC having this issue? Well, if you think about how a typical adaptive MCMC method works, what you're going to do is you're going to learn this kind of global scale quickly, and that's typically just based on targeting a desired acceptance rate, and then while you're doing that, you're on the fly trying to learn a kind of preconditioning matrix, capital sigma, using the history of the chain. And as you do that, you'll adjust this little sigma at the same time, and eventually you'll get to good values for both. But it tends to be that if you have to choose a global value of sigma that is really small, in order to get any kind of movement at all in the chain, then it then takes a long time to learn the right values of the preconditioning matrix. So I'm illustrating this with this example here. So we've got a kind of two-dimensional Gaussian example, and I've just drawn a one sigma ellipse here. And the marginal variance ratio here is 100. So in the y component, it's 100 times larger variance than in the x component. So what an adaptive algorithm will do is quickly tune the step size so that you can appropriately sample in the smaller component. Otherwise, you just won't accept any moves. But then because you've got a step size which is much too small for the larger component, it takes quite a long time to explore this coordinate and realize that actually you can precondition in a way that you're exploring much further here. And you can see that in this example here, that after I probably got about 100 iterations here, a few more iterations here, a few more here, and a few more in the bottom right. But we're still not getting anywhere near the right kind of variance ratio. So we still haven't managed to learn the correlation structure and the covariance structure of the targets to effectively precondition. And what we argue is that this is a much bigger problem if your algorithm is really sensitive to having too big a step size. Because if you can get away with having a slightly bigger step size than optimum, then that means that you start exploring the bigger components much faster. And you will see in some of the experiments that I'll show you later, and in the paper in particular, that this has profound effects for adaptive MCMC. So how do we study this phenomenon mathematically? Well, what we're going to do is try and characterize it through the spectral gap of the Markov chain. So for those of you that are not familiar, I'll talk about it more on the next slide, but essentially it's a measure of performance, and bigger is better. You know, a bigger spectral gap is better. So what we want to do is we want to fix the step size and also the preconditioning matrix of an algorithm, and then we're going to change the target distribution scales. Right? We're going to make the target distribution narrower and narrower in one particular dimension, or in L dimensions, and then we're going to see how performance degrades. So this is simulating a scenario where you've chosen much too big a step size. Right? So we want to see how fast the spectral gaps decay to zero as this degree of mismatch between the step size and the scale of the target increases. And what we find is that for the random walk metropolis, the spectral gaps decay to zero polynomially fast in this parameter. Whereas for Mala and HMC, it's exponentially fast, so it's much faster. So there is a kind of dichotomy between the two sets of approaches, right? And we argue that this is bad. This sort of formalizes the idea that Mala and HMC are more difficult to tune, more sensitive to the tuning. So the penalty is much more severe. So just a little bit more detail about the setup, because I'm aware that this is a more technical conference and there are going to be some more theory-inclined people listening. So the spectral gap of a Markov chain of a reversible Markov chain can be characterized like this. So you've got a class of functions that you're worrying about. These are mean 0, variance 1, and square integrable with respect to pi. And we're looking at how much the next point in a Markov chain, which is going to be y, differs from the current point, which is going to be x, but not just how y differs from x, but how f of y differs from f of x. We're looking at that squared difference, and we're taking the smallest one out of all the possible f's in the class that I'm looking at. So you can think of it a little bit like an expected squared jump distance, but on kind of the f projection, right? On the f transformation of the chain. And so you can see intuitively that if you've got a bigger spectral gap, it means in this kind of worst case way of looking at the Markov chain, you're going to be moving more quickly and moving around the space more quickly, and that's probably a good thing to do. In terms of the model problem setup, we've fixed the tuning parameters and we take a particular distribution, and so you could imagine that we've chosen these tuning parameters to be optimum for an algorithm exploring this distribution. And then we keep those same tuning parameters and then we change the target, right? So then you no longer have optimal tuning parameters, and they become increasingly less optimal as you make this lambda smaller and smaller and smaller, right? Yeah, so, and then we compare how the spectral gaps depend on this lambda. So a natural question, having done this analysis, is to say, well, okay, now we can see that gradient-based methods seem to be a bit less robust, but we also know that they're a little bit more scalable. So can we get the best of both worlds? Can we develop a gradient-based method, so something which has better high-dimensional scaling, but that keeps this kind of robustness to tuning of the random walk metropolis? And the answer, of course, is yes, we can. So what we want to introduce is this kind of Barker proposal scheme, and it has the same scaling behavior as Mala, so it's d to the minus 1/3, just like Mala, but it has this kind of robustness to tuning properties of the random walk. The spectral gap decays polynomially in the sense that I talked about before. And so just a simple illustration of how it works in one dimension without worrying about preconditioning, although this can all be done, and we explain how in the paper. So just an illustration, we start by drawing some random noise, random zero mean symmetric noise, just like you would in the random walk or in Mala or HMC. And then we draw this other random variable b, right? And we're going to make it +1 or -1, and whether or not it's +1 or -1 depends on the gradient of log of pi, right? So that's where we get the kind of informedness in the proposal. And we're going to set y to be x plus b times xi, right? So the idea is that this variable b decides whether or not we should flip the sign of our random noise. So we're just working in one dimension here for now. And yeah, if the idea is xi might be going in a good direction or a bad direction, and b is going to help us steer it in the right direction. So just breaking it down a little bit more, well, if you draw some random noise and it's positive, and the gradient is also positive, so it's telling you go in the positive direction, then they'll have the same sign, and that means that the probability that b equals 1 is going to be greater than 1/2. So most likely you're going to go in the direction that xi wants you to go in, right? So you're going to move uphill. Similarly, if they have the opposite sign, right? So if xi turns out to be telling you to go in a downhill direction, i.e. contrary to the gradient, then b is going to be more than likely -1, right? So you could still go in that direction. Of course, you need some kind of stochasticity, but the probability of b being -1 is going to be greater than 1/2. So you're more likely to go in this direction. So the proposal ends up being skew normal, right? So you're starting with a normal random variable, and then you're skewing it in the direction of the gradient. And this is the key distinction between this Barker scheme and, let's say, Mallet, right? Because if we look at what's happening in Mallet, you take the current point, you add xi, and then you have some kind of deterministic drift in the direction of the gradient. And here we're doing something quite different, right? We're taking xi and then we're skewing it. And it's this skewing that really gives you the kind of issue. So it recovers this kind of robustness that you don't have with Mallet, because it's this kind of extra term here that can be a little bit unwieldy to deal with, the way the gradient is dealt with in an additive way. And that's exactly the same in HMC. If you break down the HMC algorithm, the gradient steps are taken in a kind of additive way. And this can be extremely beneficial, but it does also make the algorithm sensitive to tuning. So just a toy example, just pictorially to picture this, imagine we're sampling from this rather simple standard Gaussian target distribution in one dimension, and the current point is here. So we have this gradient, it's telling us to go in that direction. And let's say we draw some random noise and it ends up being -1.2, so x plus c is going to be here. Well, this is good, right? Because xi and the gradient kind of agree, they're both negative. So if we calculate the probability that our b is going to be 1, it's 0.96. So with probability 0.96, that will be the proposal, right? And if we, by some chance, 4% chance, we decide to flip the sign anyway, then our proposal will be over here, which will be 2.8 plus 1.2, right? So 4. So if you look at that on aggregate, what happens to the proposal kernel? Well, you see that you get this kind of skew normal distribution as the proposal. And of course, you don't need normal as the base kernel, but we're just keeping it here. You'll always get a skew symmetric distribution. And the red lines of increasing sort of intensity and increasing level of skew characterize what happens depending on the magnitude of the gradient. So it's important to note that we are using both the direction of the gradient and the magnitude of the gradient to inform proposals. And that makes it slightly different from schemes like the kind of truncated metropolis-adjusted Langevin algorithm, where you're really only looking at the direction. So this is a departure from that. We are using all of the information of the gradient, and that, I think, is why we get the good scaling of Mallet. So, of course, I've only shown you one dimension. In more than one dimension, we implement the scheme component-wise. So we have a vector of b's, and we choose to flip each. We choose whether or not each b should be 1 or -1 independently of the others. We talk a lot in the paper about different ways you could generalize the algorithm to more than one dimension, and this turns out to be the most principled. So, okay, so I've introduced a scheme, and it seems like I've just pulled it out of nowhere. Of course, we haven't pulled it out of nowhere. You can relate this, just like Mallet and HMC, to a pi invariant stochastic process in continuous time. And in this case, you want to think about jump processes. So here's a family of continuous time Markov jump processes. that have the following generator. And if you play some tricks, you slightly approximate the process. So we've got this G function here, which is known as a balancing function. And if you rewrite the context, if you choose Q to be symmetric and then you rewrite the inside of this G, the argument, and make a Taylor series approximation, you can uncover what looks like a gradient. And then if you choose a specific value of G, and in this case we've chosen it to be exactly Barker's dynamic from Metropolis Hastings, from the Metropolis Hastings algorithm, then you are going to recover the Barker proposal scheme. So that's where the name comes from, and this is the kind of pi invariant process on which it is based. And surprisingly enough, you can actually recover Mallow using this class of jump processes as well. If you choose a slightly different balancing function, the square root, and you do the same kind of Taylor series approximation, in fact, you recover Mallow. So it's a very interesting class of processes that we're hoping to study further. And I do want to give a little shout out to Sam Power and I think Jacob Goldman, who were the first people to really think about this class of processes in the context of discrete state spaces. So if you're interested in this stuff, one place you could have a look at is this paper here, and maybe Sam's talking about it at this conference or in a different one. So just to finish off, I want to give a quick application. There's obviously many more in the paper, but I've chosen a Poisson random effects model here. We've got three schemes, Mallow, random walk, and Barker, to visually compare here. And these two first plots here are characterizing how quickly the tuning parameters stabilize. Right? So we're learning these things adaptively, and it's showing you how long it takes for them to learn good values and settle. And then the bottom two are trace plots of different parameters of the model. So what you can see from looking at the trace plots first is that Barker seems to be doing the best, right? It seems to be mixing reasonably well in both mu and eta 1. Whereas Mallow eventually will get there, but it's struggling at the moment. Random walk does seem to reach a reasonable region, but because it's quite a high dimensional example, I think we've got 100 dimensions here we're working with, then it is struggling a little bit compared to Barker. And you can see the reason for Mallow's poor performance is that it's really struggling to adapt. Right? The tuning parameters are taking a really, really long time to settle down. And by contrast with Barker, things are working much more satisfactorily. Right? So of course, this is a well-chosen example to illustrate the point. But we can have a look a little bit further at some of the more numerical comparisons. So here we've got a few different bits of information, but what to focus on probably is the ESS per gradient evaluation, which we think is a fair comparison between different gradient-based algorithms to some extent. And so we've got three different scenarios, and this is three scenarios where the tuning parameters, the true parameters that we're trying to infer are different. Right? So it's increasingly difficult settings for gradient-based methods. I've highlighted Barker and NUTS. Right? So this is the Stan implementation of NUTS as the two schemes that we want to focus on. And we can see that in some settings, NUTS is doing about twice as good as Barker in terms of this metric. But as we sort of increase the challenge for gradient-based samplers, we make the gradients a little bit more unwieldy. We can see in scenario 3 that Barker's doing quite a lot better. So I don't want to claim that this is going to be better than NUTS in general. I'm trying to illustrate as fairly as I can that there's some settings in which this is going to be a favourable thing to do. So yeah, just to finish off, thank you very much for listening to the talk. I hope you enjoyed it. I'm certainly not saying that everyone should stop using things like HMC and Mallow. I like both those algorithms a lot. I've studied both those algorithms a lot, and I will continue to use both those algorithms. But Barker is simple, it is robust, and I think we've shown that and that it's efficient too. And so I think there is a place for it. As I mentioned before, it's got the same kind of scaling as Mallow. We're sort of thinking about whether we can create a version which has the same kind of scaling as HMC, so that's future work. We also look at geometric ergodicity in the paper, and we find that the kind of challenges of light tails that Mallow and HMC face, we can overcome them as well, and that's not too surprising, as the arguments are related to the arguments on robustness to tuning. They're not identical, but they are related. And yeah, of course, there are several open questions. that we're looking into now, and I'd be happy to talk to others about them. So that's all I've got time for today. Thank you very much for listening again. And if you're interested, please go and check out our preprint and email us. Thank you.